Why is the sim-to-real gap a problem for robotics deep learning? Have you ever wondered why robots trained in virtual environments sometimes struggle in the real world? This is a key issue known as the sim-to-real gap. It highlights the differences between simulated training environments and the unpredictable conditions robots face in reality. When robots are trained using simulations, they often perform well in those controlled settings. However, once they enter the real world, they can encounter unexpected challenges. This happens because simulations cannot perfectly mimic every aspect of the physical environment. Factors like lighting changes, sensor inaccuracies, and unmodeled interactions can create a mismatch. For instance, if a robot learns to navigate in a bright, uniform setting, it may struggle in a dimly lit or cluttered space. This discrepancy leads to what experts call a distribution shift. Essentially, the data robots encounter in real life is different from what they were trained on, which can result in poor decision-making and actions. This issue is particularly prominent in tasks involving deep reinforcement learning and vision-based systems. Robots often relying on camera images or sensor data to make decisions. Even small pixel-level differences between simulated and real images can confuse the algorithms, leading to failures in tasks like object manipulation or navigation. While training robots directly in the real world might seem like a solution, it is often impractical. Real-world training requires significant manual effort and can take a long time. Simulations provide a faster and safer way to train robots, but addressing the sim-to-real gap is essential for successful deployment. Recent strategies aim to bridge this gap. One approach involves using semi-virtual environments that combine simulated sensors with real robot movements. This helps reduce the differences between training and real-world conditions. Another method is decoupling feature extraction from policy learning, allowing parts of the model to be fine-tuned using real data without starting from scratch. Data augmentation techniques can also help make simulated data more representative of real-world scenarios. By increasing the variability in training data, robots can learn to adapt to different conditions. Additionally, increasing the frequency of model inference during deployment allows robots to adjust more quickly to real-time changes. Ultimately, the sim-to-real gap poses a challenge for the effectiveness of deep learning in robotics. It creates a disconnect between training and real-world performance. Overcoming this gap is vital for enabling robots to learn complex tasks in simulated environments and execute them reliably in the real world. This area is a major focus in the field of artificial intelligence for robotics, as engineers and researchers work to make robots smarter and more capable in everyday situations.